Okay, hello friends. In this session, we are going to discuss about future abstraction and manifold learning. The overview of this topic is future selection, future abstraction, future transformation, and manifold learning. Okay, let's go to future selection. First part. Okay, it's crucial to ensure that your analytic team is uncovering actionable rather than interesting data. Knowing the difference between interesting data and useful data amongst the important aspects in machine learning are future selection and future abstraction. Problem of selecting some subset of a learning algorithm's input variables upon which it should focus attention while ignoring the rest. In other words, dimensionality reduction. And the next, future selection optimality. In real-world applications, this is usually not possible. For most problems, it is computationally intractable to search the whole space of possible future subsets. One usually has to settle for approximations of the optimal subset. Most of the research in this area is devoted to finding efficient search heuristics. Variable ranking and future subset selection is the process of ordering the futures by value of some Turing functions, which usually measures future relevance. A simple method for future selection using variable ranking is to select the k highest ranked futures according to S. This is usually not optimal, but often preferable to other, more complicated methods. It's computationally efficient, only calculation and sorting of n scores. Ranking criteria, correlation criteria, and information theoretic criteria. Okay, let's discuss about information theoretic criteria. Mutual information can also detect non-linear dependencies among variables, but it is harder to estimate than correlation. It is a measure for how much information two random variables you share. Okay, future selection. Let us see full future set. This is the original data set, and then we see identify usual features. That is, we are extracting only some what we want. We are extracting in it in identical usual feature. Select future set. What we are selected is displayed in this selected feature set. Okay, then next. The goal of future subset selection is to find the optimal future subset. Future subset selection methods can be classified into three broad categories that are filter methods, wrapper methods, and embedded methods. For future subset selection, you would need a measure for assessing the goodness of a future subset, scoring function that is. A strategy to search the space of possible future subsets, finding a minimum optimal future set for an arbitrary target concept. Okay, is hard. It would need good heuristics. Filter methods. In this method, select subsets of variables as a pre-processing step, independently of the user classifier. It would be worthwhile to note that variable ranking future selection is a filter method. Let us see the diagram. It's a flow chart. Input futures, input variables. From we get a future subset selection. From future set, we get a learning algorithm. This is the filter methods, future subset selection method. Key features of filter methods for future subset selection. Filter methods are usually fast. Filter methods provide generic selection of futures not tuned by given learner. Filter methods are also often criticized. Filter methods are sometimes used as a pre-processing step for other methods. Wrapper methods. In wrapper method, the learner is considered a black box interface of the black box. Black box is used to score subsets of variables according to the predictive power of learner when using the subsets. Results vary from different learners. One need to define how to search the space of all possible variable subsets, how to assess the prediction performance of a learner. Now let's discuss about wrapper methods, future subset selection method, embedded methods. Embedded methods are specific to given learning machine. Performs variable selection in the process of training. Example, WinNow algorithm, linear unit with multiplicative updates. Summary, correlation and mutual information between single variables and the targets are often used as ranking criteria of variables. One cannot automatically discard variables with small scores. They may still be useful together with other variables. We discussed the three methods for future subset selection, that is filters, wrappers, and embedded methods. To start, I wanted to review three similar different tasks: future abstraction and future engineering, future transformation, and future selection. Now we discuss about future extraction and future engineering. Transformation of raw data into features suitable for modeling. And then future transformation of data to improve the accuracy of the algorithm. And then future selection. Removing unnecessary features. This article will contain almost no math, but there will be a fair amount of code. Let's see. We have to import the data sets like import numpy as numpy. We already know that. Let us take a text having 3 vectors. I have a cat, he have a dog, and he and I have a cat and a dog. Let us execute the code first of all. I will explain it in detail. Okay, in this we get output as in the form of numeric forms, that is in a matrix form. First of all, here we get a 1. That means in the text I have a cat. In the first vector we have I repeated only one time. In the second vector we have no repeated of I. You see that? And then in third vector I had repeated only once in a second column. That means here we discuss about how many times the word is repeating in this program. In this we write the functions for the above code, that is it will separate the words and count the number of words in our text. That is we get as output. And this is about our code. Extracting the data features from the given text. That's it. Now we discussed about text, and now we want to discuss about images. Working with images is easier and harder at the same time. It is easier because it is possible to just use one of the popular pre-trained networks without much thinking, but harder because if you need to dig into the details you may end up going really deep. Let's start from the beginning. This is something same as the text. Okay, let's discuss about the geographic data. Geographic data is not so often found in problems, but is still useful to master the basic techniques for working with it, especially since there are quite a number of ready-to-use solutions in this field. This is also same as text. And the next, we discuss about date and time. On what time and date we want to extract the data. This is about date and time simply. Now time series and web, etc. Okay, let's discuss about time series, web, etc. Regarding time series, we will go on in too much detail here, most due to my personal lack of experience, but I will point you to a useful library that automatically generates features for time series. If you are working with web data, then you usually have information about the user session. It is a wealth of information. First one is to extract the operating system from it. Secondly, make a feature is mobile. Third, look at the browser. Okay, this is something feature extraction. And now we discuss about feature transformations, normalization and distribution. Okay, now let's discuss about feature transformation. Feature transformation of data to improve the accuracy of the algorithm. Monotonic feature transformations is critical for some algorithms and has no effect on others. Feature transformation techniques, normalization and distribution, filling in the missing values, features selection. Now discuss about normalization and distribution. Monotonic feature transformation is critical for some algorithms and has no effect on others. This is one of the reasons for the increased popularity of decision trees and all its derivative algorithms. Not everyone can or want to tinker with transformations, and these algorithms are robust to unusual distributions. Now let's discuss about the code. Okay. See the code from sklearn preprocessing import standard scalar. That's the data set we have to import it. Let's see data equal to np.array of some random values with 1, 0, 0, so on, etc. and with a higher value of 100 and dot reshape of -1, 1 dot hash type np.float 64. We have to reshape the values from -1 to 1, that is, and then print standard scalar dot fit underscore transform data, that is, we have to fit the data in a standard scale and transform the data. That is, let's run the code. Then we get the data in the form, see the output -0.31, -0.31. That the output we'll get it in a form of scale, updated scaling, and we get the value, see the values approximately. Okay, that's it. And then now we discuss about filling in the missing values. Not many algorithms can work with missing values, and the real world often provides data with gaps. Fortunately, this is one of the tasks for which one doesn't need any creativity. Solutions pandas data frame, we know that pandas data frame and SQL under preprocessing imputer. That's imputer, okay? These solutions do not have any magic happening behind the scenes. Approaches to handling missing values are pretty straightforward. Encode missing values with a separate blank value like a n by a for categorical variables. Use the most probable value of the future mean or median for the numerical variables, the most common value for categorical variables, or conversely, encode with some extreme values, good for decision tree models since it allows the model to make a partition between the missing and non-missing values. For order data, okay. Easy to use library solutions sometimes suggest sticking to something like df equal to df dot fill na, that is na of 0, and not sweat the gaps. But this is not the best solution. Data preparation takes more time than building models, so thoughtless gap filling may hide a bug in processing and damage the model. Now we discuss about the feature selection. Why would it be necessary to select features? To some, this idea may seem counterintuitive, but there are at least two important reasons to get rid of unimportant features. The first is clear to every engineer. The more data, the higher the computational complexity. As long as we work with toy data sets, the size of data is not a problem. But for real loaded production systems, hundreds of extra features will be quite tangible. The second reason is that some algorithms take noise, non-informative features as a signal and overfit. Okay, this is about feature abstraction, that is feature selection, feature abstraction, and feature transformation. And let us see manifold learning in another video. That's it. Bye.